All right, we are moving on to Chapter 12. Chapter 12, we're going to be looking at conditions necessary for static equilibrium. And then we're going to look at some material properties. So static equilibrium, the idea here is, well, if we build a bridge or a bunch of buildings, we would like them to be stable. We don't want them falling down. And so static equilibrium has to do with looking at structures and analyzing all the forces. Now there are also examples with, within in physical therapy, for example, where you're thinking of what forces are acting on different muscles or different bones. And so we can analyze the situation and decide how much force might be needed or might be acting on different parts of some anatomy. So anyway, let's take a look and get started with Chapter 12 here. So we're used to static equilibrium at some level. And that is, here's a textbook, it's sitting on a table. Here's the textbook, it's sitting on the table. And what we've got is the textbook. If we analyze the textbook, there's a normal force, there's a gravitational force, and what we have found is that the normal force will balance the gravitational force, and there's no net force, and so the object doesn't accelerate. The object is already at rest, so if it's not accelerating, it's going to stay at rest, is the idea. So the first condition for equilibrium would be to have all of these forces cancel out. We need to be able to do force diagrams very reliably and figure out how much force is required to make sure that things are staying in static equilibrium. So here's an example of that. Here is this chandelier. Now the chandelier is 200 kilograms. That's going to create, if I think in terms of mg, the chandelier has a force of mg. There's a tension in this cable. And so this is going to be at 1960 newtons. That's the amount of force needed to support 200 kilograms. The force of gravity is going to be mg, and that mg will be 1,960 newtons. Now, they're going to suspend this, not just directly to the ceiling, which I think looks better, but they're going to suspend this by pulling it to the side. So they'll have one cable that comes down 60 degrees compared with the ceiling, and then they'll have a tension in this cable pulling the chandelier out to the side. So what they want us to do is go in and determine how much tension we'll need. Because, well, we need to calculate the tension here too, that's 1960. We want cables that are going to be able to support the chandelier. If we don't provide cables that can support this much force, then the cables will fail, they'll break. And that's a pretty big chandelier. That could be catastrophic. So let's take a look and see. Here is a force diagram acting on nothing, sort of. So what we've got is, if we go back and look here, we can say, what objects could we look at to try and analyze what the forces are going to be? Well, we could isolate the chandelier, and we'll do that. But the second point we're going to isolate is where all the cables come together. Now, there's no object at that location, but it's still a point where we can go in and analyze forces. So here is the chandelier. I separated that out. There's a gravitational force of mg. The chandelier is 200 kilograms. mg is 1960 newtons. There is no acceleration taking place, kind of throughout the whole chapter, no acceleration. This is static equilibrium. And so the tension will be 1,960 newtons. That's telling me how much tension we have in this cable right there. Now, that takes care of one cable, but now we move on to a separate point. So now we're going to move on to this location right here, and we're going to say with a tension of 1960 newtons here, and a force A at 60 degrees, and force B, how can I make those three forces balance out? How can I maintain static equilibrium? How much force do I need? How much tension do I need in cable A? How much tension in cable B? So I took this force diagram and redrew it here. So what we have now is, here is force B, here is force A, this will be force A cosine theta. And the vertical component will be FA sine theta. Now I haven't written those in, but what I've done over here is say the forces in the x direction have to add up to be 0. The forces in the y direction have to add up to be 0. And that means that if I look at the horizontal components, I've got FA cosine theta here, and I've got FB to the right. So those two forces have to be set equal to each other, the cosine theta component of A and the force of B. Now in the vertical direction, force A sine theta has to equal tension. So you can see what we've done here by building the chandelier, or setting up the cables, and pulling it to the side. That's actually going to create a higher tension in cable A. Cable A is going to be under a larger tension because of the way we designed the cables. So let's see by how much. Force A can be calculated by taking mg, or the tension, those we've calculated, and divide through by sine of theta. So dividing through by the sine of 60 degrees, it says that the force of the cable in this direction, the tension, needs to be 2,263. So we're going to need additional tension in that cable. We have to make sure that cable can support the additional tension. And how did that happen? Well, it was by taking this side cable and pulling it to the side. And what happened is that now, instead of this cable by itself supporting the weight, this cable needs to be able to support the weight of the chandelier, the gravitational force, but it also needs to be able to offset that force FB. All right, so we were able to go through and show that FA is equal to 2,263. What about force B? Well, force B is going to be force A times the cosine of theta. So that sideways cable, that's going to need 1,132 newtons. That's not a small number. That's a good amount of force inside this cable that we're using to pull this to the side. All right, so that's our first example, looking at just balancing out forces. Now, we've done stuff like that before, so I feel kind of like you guys probably could have already done that problem, right? Maybe. Now, there's another condition. There's a second condition for equilibrium. It's not enough to just say that the forces have to balance out. We also have to show that there is no net torque acting on the system. So what we've got is, we got this table, maybe it's frictionless, we've got this ruler, and what we're going to do is we're going to exert some forces on it. So if we exert forces according to the diagram that we're showing, there is no net force. The forces balance out, but because the forces don't line up with each other, there will be a torque. So we need the sum of the torques to be equal to 0, but in this picture they're not. The sum of the forces, we can ask, is the net force 0? Yes, it is. Is the net torque 0? No, it's not. So this ruler is going to rotate. It's going to go into rotational acceleration. That's not static equilibrium. So it's going to be required for us not just to look at forces, but to look at torques. And that's why we waited until after chapters 10 and 11. In 10 and 11 we learned about torques. Now that we have studied torques, we can go in and analyze the situation, make sure that there are no torques taking place. Now here's an example. This it says is a conceptual example, but what we're doing is there's an enormous boulder here, a rock, a small rock. Oh, the small rock is here. So the small rock is here, and that's the large rock. And what we want to do is pry this up, so maybe push the rock down the hill, I don't know. So we're going to lift this really large rock. Now it's really heavy. What we can do in terms of torques though, is, let's think about this. If we get something really sturdy, here is this steel bar, and it's really long, and so what we can do is put a rock, a small rock, near the larger one, push the steel piece underneath, and then from the other side push down. Now what does that do? And it amplifies the force. This is remarkable. But let's say that the rock has a gravitational force acting on it of mg. We need to be able to offset mg in order to lift it. And so we can look at the torques on the two different sides. Now the force we are going to, or the torque we are going to operate with, the torque on this side is going to be mg times r, and the torque on the other side is going to be big F times r. And when we push down and set up those torques, it says that the force we are going to be pushing with in order to lift the rock, in order to balance out the torques, we just need to lift with mg little r over big R. Now mg is huge because it's a really big rock. But if we make big R much larger than little r, the way it's set up right now, it looks like big R is maybe twice the length. That would give us an operating factor of, a leverage factor of 2. So that would mean that we can actually lift twice as much as we would have been able to lift otherwise. Now if a factor of 2 is not enough, we can get a longer steel bar and we can push down. At some point, you're going to have enough leverage in order to move that rock. You just have to find a steel bar that's long and rigid. All right, so here are some recommendations, and we really haven't done many problems yet, so I think it's a little early to be looking at recommendations. Choose one object at a time, use free body diagrams, make sure you're clear about coordinate systems, write down equilibrium equations. Okay, we'll talk about these as we look at some examples. Okay. All right, here's an interesting example. We have a couple kids here. One is 30 kilograms, one is 25 kilograms. And what we want to do is find out where the 25 kilogram kid should be sitting in order to balance the teeter-totter. So let's see, the board itself has a mass of 2 kilograms, but the board doesn't come into play because we're going to balance the board in any case. So the teeter-totter board is set right in the middle, and so the teeter-totter board by itself is not going to tend to lean to the left or lean to the right. It's just going to tend to stay balanced. Now what is going to happen is that when the kids climb onto this board, that's going to create a torque. There's going to be a gravitational torque of mg on side 1, and that is going to get multiplied by lever distance 2.5. Now on the other side, remember this kid is heavier, right? 30 kilograms. Oh no, A is heavier, 30. Yeah, the numbers are here, sorry. 30 kilograms and 25 kilograms. And so we're trying to figure out what the lever distance needs to be on this side, because we've got a different gravitational field there. So we're expecting that on side 2, on the side of B, the distance is going to have to be a little bit bigger. So here we go. Here's the diagram. Let's take a look at the torques being created. Now the axis of rotation is right there. The torque we're going to get from side 1 is M1G_R1, which is in the picture here. The torque we're going to get on side 2 is M2G times R2. These torques are opposing each other. They're in opposite directions. And that means I just have to make sure I have the same magnitude, the same amount of torque on each side. So we can take M1G_R1 and set it equal to M2G_R2, and the G's will factor out. I'm left with R2 is equal to R1 times M1 over M2. So I can look at the ratio of masses and then make sure that the ratio of lever distances is inversely proportional, is what it shows. So R2 is going to need to be a little larger because M2 was a little less. And to make sure that these balance out, R2 should be 3 meters. So that's the idea. Make sure that the torques balance out. We're going to set the torques equal to each other. Okay, so what happens in these problems? Let's see. When we start setting this up, we've got a couple of supports here. Oh, that's huge. Is this a building or something? This is like 20 meters, and that's like 30 meters. That's 50 meters across. You know, that's half a soccer field distance that we've got here. So it's some large structure. And in the diagram, we're looking at that horizontal beam, whatever that is. Now the center of mass, or the center of gravity, is over here, and that means this thing is going to tip. Now what would happen if, when I draw the force diagram, I get the gravitational force acting here, mg, and I've got a force lifting up on the object here, but mistakenly I put the force here for the support at A. Lifting up here is not going to help. I actually have to hold this side down because the tendency here is for this to tip. So is this going to be a problem if we solve with this force diagram? And it turns out it's not. If we set up the force diagram, and if by chance we get a few of the forces backwards, we'll still be okay because FA will turn out to be a negative number. When FA turns out to be a negative number, we know what that tells us is we got the direction backwards. And it's no big deal. So anyway, they're just showing that will work. So here is one of our examples with looking at bones and muscles. And the idea here is someone's forearm, and they're holding on to an object, and the object is 5 kilograms. That's really dense. I wonder what that's made out of, because it's 5 kilograms. It's not that big. Looks like it's the size of a baseball, but it has a mass that's 20 times more, 50 times more, something. All right. Here is a muscle. Here's the bicep. Now, what we've got are, well, we got a bunch of bones, right? We got the ulna and the radius. We got all the carpals and metacarpals and phalanges, and we've got a humerus here. What object are we analyzing in order to, they want us to calculate how much tension is in the muscle, and they want us to know how much force is pushing down on that bone. So that's something we got to stop and look at. And look, in part B, they're going to change the angle of the forearm and go in and reevaluate. I think we want to stick with this first. We'll come back and look at this in a minute. But what they're telling us is this. They've given us a bunch of distances and masses. So I know the person has this 5 kilogram object that they're holding on to. It says that the person's forearm is 2 kilograms, and that the center of mass, or the center of gravity, is 15 centimeters away from 15 centimeters away from the articulation between the bones right here. So I've got a point here where the humerus is exerting a force on the ulna, maybe, and that's pushing down. There's a gravitational force here, gravitational force here. There's a bunch of downward forces. So where is the upward force? And the only upward force I see is coming from the muscle. It's coming from the bicep right there. So let's take a look and see. Let's look at the numbers in terms of mass and in terms of distances. What it seems to be is that we want to look at the forearm. It looks like all of the forces that we were given. There's a gravitational force on the forearm. There's an additional effect due to the gravitation acting on that 5 kilogram object. The bone here is going to have to push the arm down while the muscle lifts the forearm up. So these two together, the bone pushing down, the humerus pushing down on the ulna, and the bicep lifting up on that arm, that's got to provide enough torque to offset the torques from these gravitational effects. That's the idea. That's how we're going to stabilize this. Now, the distances here are 5 centimeters from point A out to point B, and 15 centimeters from point A out to little mg, and 35 centimeters from A out to big mg. Now, we can write down the conditions for equilibrium. First of all the forces have to add up to be 0. That one's not that hard. It just says that FB, lifting upwards, needs to be equal to FA plus mg plus big mg. All the upward forces have to balance out all the downward forces. That's what we're saying with this. All right, now that's not enough to solve the problem. I have 2 unknowns. I only have 1 equation. So we got to move on and calculate it using torques. Now, a lot of times students, for whatever reasons, they're convinced that they can solve it just by balancing forces, and you can't do it. You have to embrace the torque formulas. You're going to have to set up torques in order to solve these problems. Now, when we set up torques, what we can do is pick a location. I could, for example, calculate all the torques around point A. Or I could calculate all the torques around point B. Or I could calculate all the torques around point C or point... So I can pick any point I want, and I can use more than one point in the same problem. So let's do this. Let's start out, and this is just a notation I use to tell myself what I'm doing. I'm going to sum up all the torques around point A and set them equal to 0. That's my intention. So the torques that we would have around point A, which of these torques are positive? And by positive we mean rotating in this direction. So the muscle, the force from the muscle, times a lever distance, that's going to be FB times 5 centimeters. That's the amount of torque we're getting from the muscle relative to point A. Now, what's going to happen is that torque is going to have to offset both of these gravitational torques. Now, the force at point A doesn't come into this formula because there's no lever distance. So by picking point A, we eliminated force A from the equation, and that means we'll only have one unknown. So that's the key here, is to pick a point that eliminates some of the unknowns so that we only have one unknown left. So that's what we've done here. Now, again, if I think in terms of this torque has to offset these guys, well, these lever distances are much bigger. That means this force is going to have to be much larger. So this force times 5 centimeters has to be able to offset the gravitational force, mg, which has a lever distance of 15, plus one more gravitational force that has a lever distance of 35. Now, I plugged all those lever distances in. We could go through and divide by 5, and it says that force B, the tension in the muscle, in the bicep, needs to be 3 times mg plus 7 times big mg. Putting all those numbers in, that works out to be 402 newtons. So the muscle actually has a tension that is many times more than the gravitational forces that we're dealing with. Okay? And that's because it has a smaller lever distance. And you think, well, that's the way arms are going to work. I can't really have a muscle that attaches way out here. The muscle attachment is going to be much closer to the axis of rotation, and then we're just going to have muscles that are able to produce large forces. So that worked really well. We were able to determine how much tension is in that muscle. That actually is now enough information that I could go in and solve for force A, but instead of doing that, let's practice looking at torques around a different axis. Point A works so well, I'm going to go on and see what happens if we use point B. Now, if I think of point B as a rotational axis, that's a little weird because I'm not thinking anything actually rotates around point B, but that doesn't matter. We still can use the requirement that the torques have to balance out around any point that we look at. So let's see what that means. Let's see how that's going to work. So if I pick this point and I start measuring torques, the positive torque is going to come from force A now, and force A has a lever distance of 5 centimeters. So force A times the 5 centimeters has to offset the torques from gravity. Now, lever distances here have also changed. The lever distance now from point B for little mg is going to be 10 centimeters, and the lever distance for big mg is going to be 30. Okay, so force times lever equals force times lever plus force times lever. Every term in that equation needs to have a force times some kind of a lever distance. When I calculate that out, that becomes Fa needs to be 2 times mg plus 6 times big mg, so that needs to be 333 newtons. Now, we've got the forces calculated. Let's check them and see if this works. So it says that the force at B, which we calculated to be 3 mg's and 7 big mg's, has to equal the force at A, which was 2 little mg's and 6 big mg's, plus mg. Yeah, it checks out. So if I now take the forces determined using torques and put them back into the force equation, they need to work. If they don't work, something's gone wrong. We have to go back and double check. Now, what happens when the arm turns and angles downward? So the arm now is going to angle down at 45 degrees or some angle. It's going to go down at some angle here. Well, the lever distances, in this case, all of the lever distances will pick up a factor of cosine theta. So there's going to be a cosine theta here, a cosine theta here, and a cosine theta here. So since all the lever distances scale down, we're going to get the same answer. It's a little weird, but that's the prediction here is, okay, here's a 5 kilogram object. I'll put that in my arm, and I'm trying to judge if it's getting easier or harder or staying the same. Our prediction here is that it would stay the same because all the lever distances end up shortening by the same amount. Okay, feels kind of like, it's certainly plausible that the tension remains the same all through this. Okay. All right, here is a hinged beam. So let's see what we've got here. Here is a sign that is being held up. There's a beam that runs along here. Apparently it has some mass. There's its gravitational force pulling down on it. Here is a sign. Now the sign has mass big M, and the effect of that is to create a force with magnitude big mg lifting down here. So I've got these two masses these two gravitational forces that we have to support. Now, we're going to do that by taking this beam, attaching a cable, and running the cable up to the side of the building, and then anchoring that into the side of the building. That's going to need to be anchored really well so it doesn't come loose. And now, the cable will have a tension, and the tension within a cable runs right along the length of the cable. Cables are flexible, which means that if I use a cable to pull on something, the direction of the force is the direction of the cable. So I know the direction of the tension, it's going to run right along the cable. Now, did they give us an angle? It said the beam is 2.2 meters with mass 25 kilograms. Oh, there we go, 30 degrees that the cable is angled at, and then the sign is 28 kilograms. So the beam's about the same mass as the sign. Sign's at 28. I'm a little worried that that sign only has one cable attached to it. I think that sign's going to get blown back and forth in the wind. It's going to spin around. Anyway, not my bookstore to worry about. Let's see. Determine the components of the force that will be acting on the beam. So, looking at everything that we set up here, I think the central object, the object we want to analyze in order to solve for tension, we want to solve for tension, and we want to find out how much force is acting on that hinge. So there's a hinge point right here, and to solve those, I think we want to look at the beam. Now, let's talk about this hinge a bit. This is sort of interesting. They've actually attached the beam by placing some kind of a support, this rounded off, and then there's a hinge so they can put a metal pin through there and hold the beam in place. Why didn't they just anchor the beam into the wall? And what happens in these static equilibrium problems is just anchoring something into the wall can create problems. So whenever you have something that's being held out like this, and like the beam would be, what we tend to do is just attach it with a hinge. So we're not trying to create torque by anchoring the beam directly into the wall. We're actually going to let the beam move back and forth freely. And what that enables us to do is leave it up to the cable to get everything in equilibrium. So this way we can get a reliable measurement on how much tension we need in the cable. So, so yeah, that's a hinge there. Now the hinge can create normal forces that push on the beam in either direction. The hinge could go push that way, it could pull the beam in, it could lift the beam up, it could push the beam down from that one location. Now what I'm seeing here is the presence of the cable is going to tend to, there's a vertical component, and the vertical component will help support the beam and the sign. There's also a horizontal component, and that's going to tend to push the beam into the building. So the hinge is going to need to offset that. The hinge needs to provide a force in the opposite direction to prevent the beam from getting pushed into the building to hold the beam in place. Now, the question I'm not sure about, well, maybe, let's see, is should this other component of the hinge force, should that be vertical or should that be down? I think it should be vertical. I think they got it right because we've got mass here that needs to be supported. We've got mass here. I've got an upward force here. Here that beam is just going to go. So yeah, I think this does need to be up. And then remember, if we get it backwards, the math will tell us that we've gotten it backwards. So that's good to know. All right, let's take a shot at it. So first of all, let's write down those force formulas. All the forces in the x direction, they need to add up to be 0. All the forces in the y direction, they need to add up to be 0. In the x direction, the only forces acting on the beam are t cosine theta. So here's the tension. Here is t sine theta. Here is t cosine theta. So T cosine theta is pulling the beam inward. Fx, I'm going to call this Fx and Fy at the hinge. I'm going to simplify the notation. So here is Fx, here is Fy. Fx needs to be as large as T cosine theta. Those two are going to match if it's in static equilibrium. Now, in the vertical direction, I've got Fy and T sine theta upwards, and I've got little m and big M downwards. So the two upward forces have to cancel out the two downward forces. Now, again, I can't solve anything from those force equations. There's just too many unknowns right now. But what I can do is I can now start using torques, and at some point I can come back and use these, or I can come back and use those as a check, just to make sure that my answers make sense. Okay, so I'm going to start with point A to measure my torques. And I want to start with point A because I don't know what Fx is, and I don't know what Fy is. The beam itself is rigid, and so it could have any component. Fx and Fy could have any values. There's no way to relate what Fx and Fy, there's no fixed value for those. The Fx is going to be dependent on T cosine theta. The Fy is going to depend on that lower equation. So that's two unknowns. If I put the torque, measure torques around point A, I can eliminate those from my equation. So let's do that. So if I pick point A, then Fx and Fy, they drop out of the torque equation. They're not going to be there. That says that, oh, and look, T cosine theta also drops out. So T cosine theta drops out. The only forces left will be T sine theta, mg, and little mg, and this is the axis of rotation. So I'm going to have T sine theta with a lever distance of L, and that's going to be in what we consider the positive direction, typically. I'm going to have mg with a lever distance of 1/2 L, and big mg with a lever distance of L in the opposite direction. So that's how things are set up. Now what happened in this case, and what happens often, is that one of these distances just factors out. The L goes away, the L goes away, the L goes away. The only thing that stays around is this factor of 1/2. So since the center of mass, or the center of gravity, is at 1/2 L, the only thing that stays around is the 1/2. So that says, solving that equation, this torque equation, the tension is going to be 1/2 M plus big M times G over sine theta. That works out to be 794 newtons. So I can go back and see what the force is for that, and I'm getting the 794 newtons. Now, once I've got the tension figured out, I'm going to go back to that equation, plug the numbers in, calculate Fx. Once I get Fx calculated at 688 newtons, I can take Fx, put that back into, oh, actually it's still the tension, huh? So once I get the tension calculated, I can plug those into here and here. Those will give me Fx and Fy. So Fy was also calculable, and that's 122 newtons. So at this point, we could take the numbers that we've calculated, plug back into any of the formulas, maybe plug back into the force formulas, and verify that all the numbers check out. Now, we didn't use any more torque equations. We only used that one torque positioning. All right, now here's another example. Here we are looking at a ladder. The ladder, it says, is 5 meters long, and it leans against a smooth wall. And its base, the base of the ladder, is oh, I'm sorry, the point of contact is at 4 meters. Now, the ladder itself is 5 meters, and there is a right triangle set up here. I think the base is going to be, the x naught is going to be 3 meters. I think we can use Pythagorean's theorem. You guys have probably seen plenty of 3, 4, 5 right triangles in your math classes. So we can use Pythagorean's theorem to determine those, that distance. Now, the ladder has a mass of 12 kilograms, and the center of mass is located right in the center. So I'm going to get an mg on the ladder. Now, it's beginning to look like the ladder itself is the central object that we want to analyze to determine all the forces. So we want to be able to find out how much force is there along the wall. Now, that's a normal force. And how much force is there vertically along the floor? That's a normal force. And then how much friction are we going to need? So assuming the wall is frictionless, determine all the forces. So how large are each one of these forces? Now, they've said there is friction here, but you know, to simplify the problem, they're ignoring any friction at this point. So, with all the information they've given us, it looks like this. It looks like, here is the ladder. There's an angle of theta where the ladder is tipped. There's a force of mg. There's a normal force at the floor. I'm calling that N1. There's a normal force at the wall. I'm calling that N2. And then N1, and the friction. Sorry, I left out friction. So the sum of the forces in x and y say this. They say that that friction force on the floor, it better be static friction force, and it needs to be as large as N2. In the vertical direction, N1 needs to be equal to mg. So those are my two force statements for static equilibrium. Now, the mass here of the ladder is 12 kilograms, and then the length is 5 meters. All right, these equations are not going to solve everything for me. I'm going to have to look at torques. I'm going to pick a point here at the floor, and that's because this point eliminates two forces. It eliminates N1, and it eliminates the frictional force. So if I think of torques around point A, that's going to be a gravitational torque in the negative direction, and there's going to be a torque from the normal force of the wall in the positive direction. Now, the normal force from the wall has a lever distance of 4 meters. Where is that in the diagram? So this problem has forces both horizontal and vertical, and let's do this. What I often find is useful is to take my force diagram, redraw it, and redraw it in a way where I can very clearly see where all the lever distances are. So what we've got now, I didn't try and draw the beam, I just drew this hypotenuse. There's an mg coming down from halfway. There's an angle theta here, there's an angle theta here, there's an angle theta here. There's an N1 coming out this direction, there's an N1 here. Now, the point we're measuring torques around is that point right there. That's point A. And so this force drops out, this force drops out. mg is going to have a lever distance of 1.5 meters. Okay. The whole distance along the floor here is 3 meters, and that comes from using Pythagorean's theorem. They told us this distance is 4, and they said that the ladder is 5 meters. So that enables us to go in and calculate the 3 meter distance. So the mg is going to, here's point A, mg is coming down this way. The lever distances need to be perpendicular. So I'm not measuring this distance for the leverage, I'm measuring this distance for the lever. and that's the 1.5. Now, as far as N2, N2 is in this direction, and if I use a perpendicular lever distance, the perpendicular lever distance will be 4 meters. So that says N2 times 4 meters needs to equal mg times 1.5 meters. Now that says that N2, and I don't know why I did a fraction, but I did. I wrote this as 3/8 mg. So N2, the force from the wall, is going to be 3/8, 0.375 times mg. So let's start writing some numbers down. Mg is 118. Now that comes from the 12 kilograms. N is equal to mg, so I already know that force. That force I was able to calculate based on the force formulas. Now N2 is going to be 3/8 of mg. That's going to be 44 newtons. And so if N2 is 44 newtons, then the static frictional force also needs to be 44 newtons. All right, so we were able to figure out that the angle here, I don't know if we ever needed this, right? The angle that we've got here is 36.9 degrees, and that came from, I guess that's, yeah, that looks fine. 4 divided by 5, and we take an inverse cosine of that. Now, is there going to be enough frictional force to hold the ladder in place? So let's check that and see. That's kind of an interesting question. What would need to be the static coefficient of friction? How large would the static coefficient of friction need to be so that the ladder doesn't slide? Now, whenever I see the ladder problem, this is a very common example that is used in physics and in engineering and such, to think about how these torques work. I also think about a bookcase, and here is a book, and I've leaned the book up into the bookcase, and they always fall over. You know, I lean the book up and then it slides over, and I always feel like it's because there's not enough friction. You know, they make these nice bookcases that are smooth and polished, and shouldn't they make bookcases with really high coefficients of static friction? Anyway, let's move on with the ladder problem here. The coefficient that I would need, let's see, the maximum static coefficient of friction needs to be at least large enough to equal N2. That would be 3/8 times mg. So the coefficient of friction then would need to be equal to the maximum value, needs to be well, the static coefficient of friction would be the maximum value divided by N1. So the way that coefficients are defined, the coefficient of friction is equal to this force, this frictional force, divided by the corresponding normal force. So it's been a while since we've looked at friction, maybe chapter 5, but we're coming back now and taking a look at this. So that needs to be F max over N1. N1 is equal to mg. F max needs to be greater than or equal to N2. So I can put this as N2 over N1. That's 3/8 mg. The mu needs to be as large as 0.375. So I need a fairly good size coefficient of static friction to make sure this ladder does not slip. And you guys have seen the ladders, you know, on the feet on ladders, they make them out of rubber or something so that you get a good grip on that horizontal surface. All right, so I did write it as the ladder / bookshelf problem. Okay, any questions on that? And again, it comes down to getting those torque equations set up correctly. So let's talk a little bit about stability and balance. What we've got here is, here's an object, there's a tension lifting upwards, there's a gravitational force down. Because the two forces exactly cancel out, they're lined up. because the two forces are lined up with each other, the tension is able to exactly offset the gravitational force. If I pull this object to the side, there's no way the two forces can cancel out. And that's because gravity continues to be downwards, but the tension is going to be both vertical and sideways. So there's going to be a net force that tends to bring it back to that equilibrium point. So the equilibrium point is the left picture, and if it tips a little bit to one side or the other, it returns, and that's considered a stable equilibrium. Well, what would be an unstable equilibrium? And that would be something where this is at equilibrium, but it's not stable, meaning if there's a small drift away from the equilibrium position, the forces do not return the object to equilibrium, they push the object away. So in the earlier example, the net force, if the system is pushed, if it's disturbed, pushed away from equilibrium, the forces return the object to equilibrium. This is called a restoring force. Here there is no restoring force. Balancing a pencil is kind of a one-shot deal where if you can get it balanced, it's there, but if it drifts a little bit to the side, it's not coming back on its own. Okay, so that's considered to be an unstable equilibrium. Now let's think about this in terms of a refrigerator. So here's a refrigerator, and normal forces all along the bottom, the center of mass or the center of gravity somewhere in the center. The normal forces could be anywhere along the bottom, and that says that if I begin pushing the refrigerator to one side, as long as the center of mass location is within the bottom of the refrigerator, it can restore itself. But once the force, you can even balance the refrigerator, right? Try this, go home and try this. Balance the refrigerator, see if it can, balance it at that one point. If it drifts even a little bit to this side, it's going to rotate. So it'll rotate over. And as they point out here, once it hits the floor, it will be stable again. You have to think of the bright side here. Here's another issue with stability and balancing. If you carry a heavy bag to one side, your posture compensates for that, right? So you shift your posture, and depending on where the weight is located and how you shift your posture, it might not be healthy long term. So I guess they're suggesting that a backpack keeps your posture, compensating for a backpack is not as difficult as an unbalanced weighting system that you've set up. All right, I think it's probably time to take a break. Yeah, let's go ahead and do that. So let's take a break right now. If you guys have questions, let me know.